Okay, so this topic is the title is kind of the art of computing an inverse of finite field, of the elements over finite field. I think last week, right, Jeff shared us with how to compute that the inverse of a prime field using either of these algorithms. The first is the extended Euclidean algorithm. The second is the Fermat-Little theorem. I'm not sure if I can remember that the formula about these two algorithms. But second kind of is relatively easy, right? For example, we have a okay, theta. Sorry. For example, a theta in some, the prime field, and then we want to calculate the theta to -1, and equals to theta p minus 2, right? Okay, it means that we just blindly compute the explanation of theta, then we'll eventually get theta to -1, because the Fermat-Little theorem tells us that theta p equals to theta, right? Mod p. Okay, it's a Fermat-Little theorem, and use that we can easily to compute this stuff. But today's topic, kind of, what we want is to going to compute the inverse of an element from an extended field. Okay, extended field like this, fp to k, it's a finite field. It's an extension field. Okay. Okay, let's begin with a very simple example. We have a quadratic extension of some prime field fp called okay, let me write here. Okay, okay, quadratic. Sorry. Quadratic extension over fp. So here fp is prime. Then we can write this p squared, right? P squared. For example, we have some element theta from p to square. Okay. Okay. Here we have to say, okay. For some general extension field, fpk can be, for example, some theta from fpk can be rewrite as a polynomial, right? Polynomial. Like a0 plus a1 plus alpha plus a2 times alpha square plus to the ak minus 1 times alpha to k minus 1. Okay. So theta can be represented as a polynomial. If we use the Fermat-Little theorem, this method to compute that the theorem to -1 equals to theta p minus 2 equals to, okay, we can say that we have to do a explanation over on this polynomial, right? Okay, the explanation is p minus 1. Then we can say that, okay, if we blindly compute this polynomial exponentiation that we got a lot of cross terms, right? So it's generally expensive to compute the explanation over a finite field of some element from the extended field. So here we're trying to simplify or optimize this process to can quickly get the theta to -1. Here is a similar example. Okay, we'll just simplify the case. That here is we only have a quadratic extension, and fp square can be constructed by an irreducible polynomial. Okay, let's write this expression here. Okay, here you see 0. Okay. We can construct this quadratic extension field fp square using an irreducible polynomial x squared minus c0. Here, presumes that 0 is element from fp. Okay. Please remember that. Keep in mind that x squared minus c0 is irreducible polynomial. And then so in the theta can be rewrite things like is a0 plus a1 times alpha. Okay, here the alpha is the root of x squared minus c0. Okay, so alpha squared equal to c0. Okay. So now we can get the representation of theta. So theta times c theta to -1 will be equal to 1. Okay. So we just assume we let the eta to -1, the inverse of theta equals to some, also because it's also an element from this finite field. So the inverse of theta can be written as b0 plus b1 times alpha. Okay. 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 Any question here? No question? Cool. So then we expand the definition of theta and the inverse of theta. Theta times theta equals to a0 plus alpha times b0 p1 alpha. Okay. And then we can have a0 b0, right? Plus a1 b0 plus a0 b1 alpha plus a1 b1 alpha square. Okay, because we already have this equation that alpha square equals to c0, right? We can. Okay, here will be a1 b1 times c0. Okay. We can have the this new element like a0 b0 times a1 b1 times c0 plus a1 b0 plus a0 b1 times alpha. Okay. Because this is also the first element of okay. Is that okay? So this element should be equal to 1, right? should be equal to 1. Okay, that means we can solve this formula. We can rewrite it as a matrix vector multiplication, so that it will be clearer. So C0 times A1, A1, A0, the B0, B1 equals to 1. So we can write this equation into an equation of matrix vector multiplication. Okay, we can easily verify, okay, this equation is equal to this equation, okay. All right. Okay, stop here for 1-2 minutes for you to verify. Okay, don't trust me, verify. So why we use the matrix equation just because we want to remove that the alpha. It's a matrix equation. And then we can inverse this matrix. Okay. Invert this matrix, and we can have to solve B0 and B1. So we're equal to A0, sorry, A1, C0, A1, A0. Right, we just inverse this matrix, then we can calculate this inverse of the matrix will be equal to here be result A0 square minus C0 times A1 square minus times A0 minus A1. A1 and then Z0, okay. Okay, this is the inversion of this matrix. Okay. Now we have the B0 and B1. So if we calculate this equation, okay. So then, if we want to compute inverse of theta, which is compute B0 and B1, and then B0, B1, we have to evaluate this equation, right? And now we inverse the matrix and we got this one. Okay, now we can say we have to do an inverse here, right? So this inverse is over the base field. It's an inverse over FP. Okay, so inverse over FP here, right? And then we just do a few multiplication. We can have the result of B0 and B1. So the process is showing that, okay, if we want to compute the inverse over an extension field, now the problem is reduced to the problem of computing inverse of some inverse from the base field. So doing inverse on the over base field kind of easy, cheap, right? It's the basic idea that, okay, how can we compute the inverse over extension field? But right now, because the extension degree is relatively low, it's only 2, degree is only 2. But it's the basic idea of that. So I'll stop here for 2 minutes. You can verify.
So question. So why the right side of the equation is 1 and 0?
Because 1, the representation of 1 in here is 1 plus 0 times alpha. Okay. So now the computation task is reduced to, we have to compute this inverse over base field, but the inverse computation is over base field. Okay, now we can use either format little theorem or extended Euclidean algorithm to compute this inversion. Okay. Okay.
So if we do it on a larger extension field, so for example like P cube, so we will
cubic, okay.
So we will have a bigger matrix, right?
Yeah, bigger matrix. Yeah.
So for the bigger matrix, we also can find an inverse belong to the base field, right?
Yes.
Okay, so now we only need to calculate the inverse in the base field, and that's all. Right?
Yeah. Yes, you got it. And because we just use this form of reducible polynomial, so maybe you're wondering that if we can use, for example, another form of reducible polynomial. I think the idea is similar. That is similar, except that this inversion of matrix is kind of more complex. Okay, so I don't show that case. So let's move on.
If the
irreducible polynomial
is not this such as x
minus 0, yeah.
x power plus.
For example, it's like this, right?
Plus
C1 x minus 0. Okay.
So the compute will be a bit more complex.
A little bit more complex, but not too much.
Yeah, because we need to equal alpha power to.
Yeah, here alpha square will be equal to
Yes.
kind of term involves C1.
We need to compute a more step.
Yes. Yes, but not too much.
Okay.
Yeah, we can still use the similar idea.
So if get to the higher degree.
Yeah, we will show that. I will show that. Okay, let's move on to the cubic extension. Okay. Okay, cubic extension. Cubic extension. Let's see. The cubic extension. Okay. Okay. For example, some theta from fp cube, and it can be constructed as a p. We'll still use this kind of polynomial, irreducible polynomial. It's called a binomial polynomial. Binomial. Okay. Here is alpha. We will have alpha over the extended field, and then alpha and have a cube equals to C0. Okay. And then. Okay, just similar idea. Just write down the matrix. Okay. The here in the matrix is that if inverse of theta equals to b0 plus b1 plus, sorry, alpha plus b2 alpha square. And theta equals to a0 plus a1 times alpha plus a2 times alpha square. Then we can write the matrix vector multiplication for their product. Okay, looks like this. Okay, a little bit more complex. Sorry. A0, A1, A2, C0, A2, A0, A1, C0, A1, C0, A2, A0. Okay, times B0, B1, B2, and equals to 1, 0, 0. Okay. Now we compute the inverse of this matrix. We have okay, just a little bit of complex. A0 cube plus C1 times A1 square cube, cube plus C0 square A2 cube minus 3 times C0 times A0 A1 A2. Okay, inverse. Inverse. Okay, this expression is kind of this term. It's similar with this term. Okay, and times a relatively large matrix. Okay, let me just write the first column of this matrix. A0 minus C0 times A1 A2 C0 this A0 times A1 square A0 A2. Okay. Okay, this matrix looks like this, and this 6 elements kind of not interest because all this will apply 0 will equal to 0, so we just care about the first column of this matrix. Okay, this is an expression of how to compute that the the inverse of theta in a cubic extension. Still, we reduce that the inverse of extension field element to inverse of some element from the base field. Okay. I won't show you the quartic case. Yes.
We always assume this matrix is
Reversible.
Yeah.
Good question. Okay, good question.
Maybe it can be proved that it will be reversible always.
Yes.
I don't know what you said.
Yes, you are correct. Yeah. Okay, I can't answer you right now. Very good question. Okay, so how about the quartic extension? The quartic extension is commonly seen over, for example, small field Fry, because small field is about 21 or 22 bits long. then to achieve the enough security bits, we have to do at least a quartic extension over, for example, M31 or Baby Bear. So quartic extension is we have to face that how to compute the inverse of a quartic extension field, extension element. Maybe I can. Okay. The bad news is that we cannot follow this idea, right? Because in the quartic extension, this matrix will be more complicated. Then, so the problem is there any way more simpler than this idea that to compute the inverse of quartic extension? The answer is for sure yes. Okay, the quartic extension. Quartic extension. For example, we have theta from P to 4. And then this field can be constructed with degree 2 quadratic extension. Okay. I can do it like this. Okay, F P, first of all, sorry. Can be like this. First of all, we build a FP2. Fpx, and then we construct p square x minus and some beta. Okay, here beta from P. Okay. Actually, we can do 2 times of quadratic extension over P. Then we can reduce that the inverse of theta to compute the inverse of some element over Fp squared. And then we do the reduction again. Then we can only compute the inverse of some element from the base field. Okay. This is the idea because quartic kind of extension can be decomposed of 2 extensions. All right. So here we'll show you one trick that we funded the trick from the RISC-Zero's code base, but I'm not sure where the original implementation from. Okay, that trick is like we just construct Fp4 directly using a degree 4 reduced polynomial. But still the polynomial is binomial. Okay, minus C0, okay. Okay. This idea is kind of similar with these ideas, but it's a little bit different. Okay. Now we can represent theta. Okay, this 2 different ideas. Okay, this one we decompose the extension, but here for this case we can use the direct degree 4 extension over IP. Okay, theta can be represented as A0 plus A1 alpha A2 alpha square plus A3 alpha cube. Okay. And then what we want is to prove the inverse of theta, but we write the inverse of theta like this, like a, a fraction. Equal to, okay, here we will introduce auxiliary element from extension field. We call it zeta equals to, here's the trick, A0 minus A1 alpha plus A2 alpha square minus A3 alpha cube. And then we just change this definition into zeta, theta times zeta. And then just because this new auxiliary element, we change the second and the fourth element, just do negation of, it's kind of a negation of this to this term. Then something will happen that something will be cancelled out. Let me show you that. So times theta with this new element will have a new term, which is A0 square plus A2 square times C0. Yeah, C0. Minus 2A1 A3 times C0 plus 2A0 A2 minus A2 square plus A square, times C0 times alpha square. So when we multiply them together, we'll have a new term where the coefficients of alpha and alpha cube kind of will be equal to 0. So we have only two terms in the product, right? Then we introduce another auxiliary element here. We call it, okay, for example, okay, here let me just introduce two more symbols for these two expressions, like zeta B0 plus B1 times alpha square. Okay, we use B0 and B1 to represent these two expressions. Okay. B1, B0, and B1. Here, we can change the expressions into this. Okay. Now introduce one more element. Eta equals to B0 minus B1 alpha square. And then we time them both. Eta, theta, B0 plus B1 alpha square times B1 minus B1 alpha square. Now, let's just simplify this expression and we can see the result. Okay. B0 square times B1 square times alpha to 4, right? But alpha to 4 here equals to C0, okay? So just change it to C0. Okay, right now, so the inverse of theta is reduced to compute this expression here, but the denominator is the inverse of base field. Okay. Then we just write some some lines of code to implement it. It's kind of easy, yeah. Just do that simple calculation. You can get this basic idea, right? Okay, let me stop here for 2 minutes. You can verify. So the idea is that we have to figure out a path that to reduce the inverse, computing inverse of element with kind of a polynomial, kind of with over a large basis that into a single element over the base field. Okay, so I should put it here. This one is a base field, element from base field. Okay. And we call D. Okay, D0 is element from P. So. Okay. Okay. Any question here?
So what's the cost to compute zeta times
Eta, right?
eta?
Okay. I think looks simple, right? It's a 4-term polynomial times 2-term polynomial. It's do the calculation, right? It's do the multiplication over these two polynomials. It'll be easier, right? The cross term is
Okay.
okay. Less than 10. Yeah.
So is here, here is a common rule about the degree is 2 power.
Yeah. Yes, you get it. Yeah. For example, in Binius is a recursive construction of extension field, and if each time the extension is always it's quadratic, and then okay, I think okay, I see your question. I think it's not. I don't know, but you can try. For example, 8-degree extension. If we can find a way like this, I think it's general. The idea is general. I think we can apply this idea for example, even larger extension. Yes, I think it's yes, but I haven't verified it. Everything's okay? Everything is fine?
Yes.
Really?
Yes.
Okay. So how about if we want to do more kind of larger extension degree? How can we compute the inverse of, for example, 5? What about 5? We cannot use this idea, right? For example, 7, we cannot use this idea. Okay, let me. Okay, is there any more general approach? Yeah, the answer is yes. The answer is yes. Okay, we will introduce the next. So the core idea is that how can we find a path so we can reduce the inverse of extended field element into inverse of base field element. So the next idea is about using Frobenius map. Sorry. or norm map to find the path. So I should introduce what is Frobenius map is. Frobenius map for any f p2k, the extension field, the k degree extension. So we'll always find a map of phi from pk to pk. Alpha sends to alpha p. So this is called a Frobenius map. So by using Frobenius map, we can find all the conjugacy class of some root of some Euler's polynomial. But it's not a topic of today. Okay.
Is that from FP mapping to FPK?
Yeah?
It's a field.
Yes, Frobenius map. Yes, it's Frobenius. Yes, Frobenius map. We just
Is mapping FP to FPK or
FPK to FPK.
okay.
So, for example, for some f alpha, we can have alpha p and alpha p, alpha to p to p to p. Okay. Using Frobenius map, we can have all the all roots of some Euler's polynomial, or it's called a conjugacy class. Conjugacy class. Yeah, it's a very important result from finite field theory. And now, by using Frobenius map, we can construct a map. We call it norm map. Norm map. Norm map is kind of give me an alpha. Sorry, give me a theta from pk. Sorry. Sorry. Norm is another map that we can map any element from the extension field to base field. Okay, we'll get it. Norm map, definition of norm map kind of having theta literally we multiply all the conjugate class of theta together, we'll have the norm map. Theta times theta p times theta p square theta p k minus 1. So multiply them together, then the value is the norm of theta. A norm of theta. And this element is in FP. Okay. And also, the norm map is a kind of a homomorphic map. So now let me just quickly prove this truth and why this expression is actually an element from base field. Okay. For any theta, for example, theta from pk, we'll have the characteristic polynomial. Characteristic polynomial. For example, let me say as fx equals to x minus theta p x minus theta p2 square. X minus say p k minus 1. Okay, so a characteristic polynomial of theta. And fx is a polynomial over fp. So fx is actually is polynomial of fx. This is that actually all the coefficients of this polynomial are element from fp base field. So the constant coefficient of fx exactly this expression. So just because fx is a characteristic polynomial of theta, then all this stuff, if we multiply together, will be an element. Will be also the constant coefficient of this polynomial, also an element from fp. So yeah, sure, we will have another trace map, which also can map any extension field element to a base field element. But here we don't use trace, but trace kind of we can see it often in extension field operations or optimizations. So yeah. Okay, no question? Everything is fine? So I just remove this part, okay. And then right now, because we already find something magically map from pk to f, then we can compute theta inverse of theta equals to theta, theta r minus 1 theta r. Okay, where's r? R equals to 1 plus p squared plus pk minus 1. Okay. And theta r is the norm of theta. Theta r is the norm of theta. So now if we compute the inverse of theta, we only compute this inverse of normal of theta. But normal of theta is an element from P, okay. It's a norm theta in base field. Okay. Now, the work remains is only about how can we efficiently compute theta to r minus 1. Okay, what about theta r minus 1 equals to theta p to square theta p k minus 1. Okay. So we'll just compare two expressions, okay, because here we have one more theta, but here because the exponent is r minus 1, so only this is different, okay. But here this element is over extension field, right? Still we have to do kind of a lot of modification over extension field elements. So this part kind of also expensive. So, but it has a simple structure. So we can rewrite it like this, and 1 plus a and times theta p times theta p theta p. Okay. We can easily write the program code for compute theta r minus 1. But here's the problem, because for each theta p kind of expensive, right? Because theta is a extension field element. Okay. Even though we have solved this problem, okay, now we can efficiently compute the denominator. But here we have to compute this part. But this part is also expensive. Because I have to do kind of p exponentiation, no, repeatedly. Okay. Okay, the final problem. How can we optimize theta p? So if we can compute theta to p efficiently, then we can efficiently compute theta, the inverse of theta. Okay, right? Now, let's look. How can we efficiently compute C to P? Okay. C to P equals to, just by definition, A1 alpha, yes, A2 alpha square to A k minus 1 and alpha 2 k minus 1 P, right? But here, over the finite field, we can have the following, because the operation explanation is kind of linear, that we can have this AP plus A1 to P times alpha P A2P times alpha square P A k minus 1 P times alpha k minus 1 P. Okay. By using such fact called freshman dream, that A plus 1 B P always equals to A P plus B P. Okay, it's called freshman dream. Okay, by using this rule, okay, A plus B to P equals to A to P plus B to P. Because P is the characteristic of the finite field. Now we can have this new expression, right? Okay. Now we should use the Fermi-Little theorem that A0 to P equals to A0. Okay. A0 for any element in the base field, right? A to P equals to A. So can remove the exponents of some coefficient. All right. A k minus 1 times alpha k minus 1 P by Fermat-Little theorem. Okay. And then we can rewrite this expression as, A1 times alpha P minus 1 times alpha. Okay, plus A2 alpha P minus 1 square times alpha square plus A k minus 1 alpha P minus 1 k minus 1 times alpha k minus k minus 1. Okay, please say, okay, this is the new coefficient of this element. Okay. So if we can efficiently compute A0, A1 times alpha to P minus 1, then we can efficiently compute all the coefficients of this term, then we'll have the result of theta to P. Okay, the remaining problem is that how can we efficiently compute alpha P minus 1? Okay. Huh. Okay. Because okay, I have added more conditions here. So if fp to k can be constructed with the px modulo some nsk minus 0, the thing will be easier, right? Because we will have some like alpha k equals to 0, right? If we have alpha k to k equals to C0, now how can we compute alpha to P minus 1? So if we have another condition that, the k divides P minus 1, then alpha to P minus 1 is C0 P minus 1 over k, over k. Okay, remember, okay, please keep in mind that we have two more conditions. So first of all is that, okay, it's extended field, we should construct this extended field by using a binomial reduced polynomial. And secondly, and the k is one of the factor of P minus 1. If P is a large prime, that I think will have a higher probability that k is a factor of P minus 1. Then we can efficiently compute alpha to P minus 1 equal to this. Okay, it's a field over Fp, right? It's a base field. Let's go back, all the way back to, okay, if we can compute this one, then we can have theta to P, right? If we have theta to P, then we can efficiently compute theta to R minus 1. And then because theta to R is a normal map from P, okay, this division kind of easy to compute. Then we got a result, theta to negative 1. Okay, that's all. Okay.
So P is a large prime and K is a kind of a small.
P, if P is small?
P is large prime, right?
Yeah, P is a large prime.
K is small.
Yeah, K should be not too large, yeah.
Yeah, so P minus 1 divided K should be also large.
Yes.
So I don't think that the final equation can be.
Okay, because I think its explanation is not that expensive. Yeah, we can use the add chain and shared by Jeff last week, and we can just use it's kind of a logarithmic algorithm to quickly compute this. Yeah. Okay, any more questions? Okay, cool.